All right, so the big mystery, of course, as I mentioned, was why would Io, this tiny moon, be so volcanically or geologically active with active volcanoes, um, and why would that be going on? And so we realized that it had to do with um, the tidal forces on Io. So Io is not. It's a a rocky world. It has the largest density. So it's closer to a rocky world than like Europa, which is liquid. And of course, it's closer to Jupiter, so it gets a greater tidal force. Remember what tidal forces are it's like we think of tidal forces, which of course cause the oceans to rise and fall. Um, you know, uh, yeah, I mean that's because of course the Earth has this huge amount of water on it, but our moon experiences a tidal force, but the moon is made of rock, and so the moon gets squeezed a little bit, but see because Jupiter is so much more massive than Io, I mean like way more massive than Io. Uh, it really squeezes Io when it gets closer or further away. So there's a squeezing and then a relaxation and then a squeezing and relaxation that goes on. And when that happens, you're causing the inside of Io to heat up enormously. So that's the cause of the volcanic activity is these tidal forces on this big rocky moon, right? And so I mean the same kind of thing would happen to our moon, if the Earth were much more massive, a lot more massive. Um, you know, but we're talking about Io and Jupiter, and so Io undergoes these volcanic volcanic activity. As I said before, at any time you can go by Io, and remember the Galileo spacecraft orbited Jupiter for about 20 years and observed lots and lots of these. When it looked at Io, it always saw volcanic activity going on. So there's these volcanic plumes when you look at it from the edge like that. There's evidence of volcanism on the surface of Io. Um, when the lava cools off a little bit and it gets darkened. Just like when you think about our moon, right? The Maria are that I mean that now that's ancient evidence of lava flow, but nonetheless, it's still evidence of lava flow. This is much younger. Of course, this is going on right now. Then we moved out to the next satellite in the Galilean satellites, and of course that is Europa. Europa is the smallest of them, and we believe that it has this liquid ocean underneath it. You can see the surface of it is relatively smooth. There seems to be these large cracks, just like ice, right? It looks exactly like ice, as a matter of fact. Um, and in fact, because the Galileo spacecraft orbited for so many years, we actually think that it, that that there's actual um, like the movement of the ice over time, and that's what's help causing some of these cracks. And yeah, so there's probably some radioactive elements inside of just like all the worlds have some radioactive elements inside them. Because there's an ocean in there, a giant liquid ocean, that radioactive material is heating the oceans, the water, and so as so imagine you have this subterranean ocean, right? And then as the ocean, the water gets closer and closer to the surface, it gets colder and colder because you're heading towards space, which is really really cold, and so this freezes over. But just underneath it, there is this ocean. Um, and one of the things that people have proposed for a long time, as a matter of fact, a very long time, is that perhaps there is life or possibility of living things in the ocean, underneath this icy cracked surface. Um, Nobody thinks it's like you know large creatures or something like that. If anything, it's probably microbial, little microbes. Um, and the reason that we believe this is not too long ago. I forget exactly when we discovered this. There are what are called extremophiles um, on the Earth, right? So these are um, life forms that live in places that we never expected there to be life. I mean, we always thought, there's going to be living, we know there's life underneath the oceans and things like that, but we always thought that there has to be you have to have, of course, a source of energy, and I mean everybody knew that, but the source of energy most people thought had to be light. But it turned out that deep in the oceans, in our oceans, on the planet Earth, there are these. They call them smokers. So deep underneath the oceans, there's these vents where hot water, and actually highly alkaline water, is coming out, and from volcanic activity underneath, uh, and so these smokers. It turned out when we had uh, equipment that could actually survive the incredible pressure underneath the ocean, when they got down to the ocean floor and observed these smokers, that there were entire ecosystems around these smokers. In other words, they had nothing to do with light. In other words, they were surviving on the heat that was coming from the smoker, and the nutrients that are coming out from that hot water. And in some cases, the water is like really really hot, like much hotter than we thought creatures could survive. Um, and so this, what I'm saying is that opened our eyes to the possibility of life in other parts of the solar system. If life took place here on Earth, maybe it happened in other areas, even within our solar system. And of course, we're looking for life in other parts of our own galaxy, but that's a different story. We'll get to that when we talk about what are called exoplanets. So this is within our solar system, and no, we won't know this until some people have proposed we send a spacecraft, we orbit Europa, and then somehow we send a spacecraft down and lands on the surface, drills through the ice, which we don't know exactly how thick the ice is. It could be many kilometers thick, right? I mean, if it's like tens of kilometers thick, how are you gonna drill through that? That's going to be really hard. But if you could somehow, maybe it's only 1 or 2 kilometers thick, and you drill through and you swim around in the ocean. You have like a little submarine and it swims around in the ocean and looking for life, looking for what we think would be microbial life, little microbes. So we'd have to probably perform an experiment to verify it. And just to let you know, NASA is taking this they're taking the possibility of life elsewhere in the solar system very, very seriously. And when the Galileo spacecraft, when it finally ended its mission, they purposely crashed it into Jupiter. They told it to plunge into Jupiter because they didn't want to contaminate Europa in particular, because they thought, if there is life down there, we should not have any kind of contact with it, or influence its evolution. And that's not the only place in the solar system where we've done that kind of thing. When we get to Saturn, we'll talk about that as well. All right, so here's the evidence for the liquid oceans, or they're just showing you the cracks here, and like I said, if this ocean is there, and there's the evidence is pretty substantial that the ocean is there. I mean, when we study the density of this moon, it seems to be mostly liquid water. Anyhow, and there's more water, as I said before. There's more liquid water in Europa than all the oceans of the Earth combined. So there's a tremendous amount of liquid water in there. All right, so whether there's life or not, that's to be determined. All right, so then we move on to Ganymede and Callisto. So they're very similar to each other in the sense that they have a lot of craters. Of course, remember, Callisto has a lot more craters than Ganymede. We think that Ganymede might have some liquid underneath the surface as well. All right, let's see. Surfaces are mostly ice. White craters are a good indication of this. Ganymede seems to be less cratered than Callisto, which indicates that there's got to be some kind of activity going on. Sometimes some kind of geological activity, or somehow if there's less craters, it means that it's a younger surface than Callisto's surface. And so why would that be? What's going on? What's driving the surface to change? There's got to be something. All right. So here they are, and there they are. There's some really nice pictures of them. Of course, they're very far from each other. This is just a nice little montage. All right, so let's see. The average density indicates their interior composition is mainly rock. They're differentiated, so we think that the more dense material ended up at the center of these moons. The rest of Jupiter's moons are much smaller than the Galilean satellites. And they are lots of them are extremely cratered. I mentioned the Almathea moons that are actually closer than Io, but there's a lot of moons. There's some that even we think are probably just captured asteroids. The outermost moons have orbits high inclinations, suggesting that they're captured asteroids. All right, so that's